The lab-wise, I think all resident students will, participate in, hands-on experiment. But DL students probably, I can only share the just data points. Okay, so, but anyways, yeah, I mean we can talk about it more later. And so, oh yeah, I forgot to mention my name. My name is Uchar Lee, and my office is on the third floor. Okay, and then office hour is by appointment via email. Okay, or like if my door is open, just feel free to stop by. Okay, it's very easy to find my office because it's right by the elevator. Okay, and then for this course, no textbook is required, but I recommend these two textbooks. Okay, the first one is Introduction to Quantum Mechanics, written by David Griffiths, and the second one is Nanoscale Energy Transport and Convergence. So, if you are actually serious about the nanotechnology or nanoscience, and I strongly recommend this textbook. Okay, and then this one is a very general textbook, and actually, frankly, if you just search on Google, you'll be able to find PDF version. Okay, so probably, and technically no need to purchase, but if you want, yes, yeah, feel free to buy that. Okay, so, and all other course materials will be provided through Sakai. For example, this lecture videos and all like PowerPoint slides and lecture notes will be uploaded on Sakai. Okay, and I'm still working on Sakai website. Okay, so I mean probably by tomorrow it'll be completely ready. I'm gonna upload the syllabus as well, so you can take a look. But anyways, almost all syllabus information will be provided or will be discussed in this PowerPoint today. So as you know, the lecture and lab hours, for lecture Monday, Tuesday, Wednesday from 10 to 10:50. Okay, so like for these lecture hours, everyone is required to attend. Okay, so if you have to leave for like personal matter or like other like businesses, just shoot me an email. Okay, so basically as long as you send me email, I'm not gonna say anything, and just try to avoid just extended absence. Okay, yeah. So, and then for lab, Thursday 10 to 10:50 and Friday 8 to 8:50. And then for this course, 2 labs are tentatively scheduled. Okay, so those are nanoparticle imaging and gold nanoparticle synthesis. Okay, and then these are to be determined. And because of that, until further announcement, basically, you don't need to show up for lab hours. Okay, so for example, definitely this week and next week, yeah, no labs. Okay, so basically that's that. And so in terms of grading, homework and lab reports are 25%, and then we'll have 1 midterm exam. Okay, that is 35%. And for this course, we are not going to have final exam, but we are going to have final project. Okay, so this one will include individual report. Okay, individual kind of final report and presentation, oral presentation. Okay, so details will be provided later, but in a nutshell, each student will select a specific nanomaterial of your interest or of your choice, and you are going to investigate its working principle and unique properties, and you are going to explore its applications. Okay, so that's going to be 40%. Okay, so the details will be provided probably in like 2 or 3 weeks. Okay, so about this, do you have any questions? Nope. Okay, so then in this course we are gonna actually try to understand nanotechnology and nanoscience in kind of both fundamentally and practically. Okay, so and then throughout this course, I'm gonna emphasize why this nanotechnology and nanoscience are important and also why we care. Okay, so for example, this governing principle in shaping the behavior of nanomaterials actually very, very different from those used in bulk materials. Okay, so in that sense, I'm gonna basically start with quantum mechanics. Okay, and then we are gonna basically learn about governing principles, and then we are gonna basically expand from that knowledge and apply to several applications. Okay, so in the sense we are gonna actually spend quite amount of time basically in learning quantum mechanics. Okay, so yeah, this one is kind of physics content, but without knowing this, you cannot really use any you cannot really understand nanomaterials. Okay, so I would say probably like a 1/3 to 1/2 of this course will basically focus on this quantum mechanics and solid state physics. Okay, so then we are gonna actually try to understand these unique properties at the nanoscale using this quantum mechanics or nanoscience principle, and then we are gonna go over some fabrication and characterization techniques, and also we are gonna go over some examples of research findings, applications, and emerging trends. Okay, and then we are gonna evaluate the potential of nanomaterials in naval applications. But for my lecture part, yeah, probably very little, but this one will be emphasized for your final project. Okay, so basically based on your choice of nanomaterials, you will kind of try to apply that to naval applications. Okay. So then let's start with a kind of definition of nanotechnology. Okay, so what is nanotechnology? That is essentially research and technology development aimed to understand and control matter at the dimensions about 1 to 100 nanometers. Okay, so that is essentially kind of nanoscale, right? Like you guys know the nanometers, right? The nanometers, that is essentially the dealing with the matters whose size are about 1 to 100 nanometers. Okay. So then, what kind of things can we do? So for that, like 1 to 100 nanometers, you cannot actually see this matter with naked eye. Okay. So because of that, you need the special tools, to manipulate an image, right? To actually see those. Okay. And also because the properties are so different from bulk scale materials, we need to basically investigate. So those are essentially part of nanotechnology. For example, understanding, creating, and using structures, devices, and systems that have a fundamentally new properties and functions arising from their nanoscale structure. Okay, even now, some new materials are being developed, and also some new properties are being developed. Okay, and then engineered actually. So that is essentially part of nanotechnology. And also, because it's so small, like we wanna image, and also we wanna manipulate matter, in a controlled manner. Okay, so and also we wanna measure those material properties. These are so small. How are we gonna measure material properties? For example, like a mechanical properties for bulk scale materials. Like you basically create like a coupon, and then you kind of put it under tensile stress tester, right? And then you kind of extend it, right? I mean, that one is kind of, it can be easily done because you can actually see it, and then you can easily machine it to a kind of desired shape. But like how are you going to measure mechanical properties of nanomaterials? You cannot even see it with naked eye. And how are you going to measure, for example, tensile stress? How can you do that, right? I mean, you can kind of already kind of see how difficult it would be, right? So in the sense, like measuring properties is actually a challenge, and developing tools for measuring properties of nanomaterials is also very important area of nanotechnology. Okay, and also, like we want to model those properties, like including optical properties, thermal, electrical, and mechanical properties. And then we need to develop a new model because, like the classical model for describing bulk materials no longer, applies to nanomaterials. Okay. So once you do that, you can now exploit properties and functions, right? And you can further engineers. Okay. And also, like now, if you kind of understand certain materials, how are we gonna kind of integrate them into larger scales, right? I mean, like oftentimes we are dealing with a bulk scale kind of objects, right? Then how are you gonna use nanomaterials kind of and create bulk scale objects? Okay, so that is essentially, like you are integrating these properties and functions into systems spanning from nano to macroscopic scale. Okay, how can you scale up, nanomaterials and maintain those unique or excellent properties? Okay, those are essentially part of also nanotechnology. Okay. So in the sense, nanotechnology is a very broad area, okay, and then we will actually see some examples in this course. Okay. So let me just kind of start with this nanoscale. I mean, I assume everyone knows, like basically millimeter is a 10 to the negative third power, and then micrometer is a 10 to the negative 6 power meter, and then nanometer is 10 to the negative 9th power, right? By the way, can you guys see this one? Is the resolution okay? Or is it too bright?
Probably kill the front lines.
Yeah, is it possible actually if we can reduce the light? I don't know if we can actually control that. Oh, okay, this is better. Oh, maybe this one will make everyone sleep. Yeah. I think this one,
On or off. I don't think there's a.
oh, I see. It's not dimmable. Yeah. Oh, that works. Oh, yeah, great. Oh, yeah, this is good. Thank you. Yeah. Okay, so then, like basically, as we scale down, like for example, if you look at this dust particle is still micrometer scale, okay, 1 to 5 micrometer. And then now, quantum electronics or like a state-of-the-art electronic device or transistor currently use like 4 nanometer, right? Like about that, okay? And then, you can actually make a letter made out of atoms, and then that size is only about 6.5 nanometers, and actually DNA is only 2 nanometer wide, and then atom, like the smallest object, that is essentially, 0.1 to 0.4 nanometers, okay, or 1 to 4 angstroms, okay. So in the sense, this nanotechnology kind of deals with this structure that is size of like this range, okay. Just to give you a perspective, like we can kind of think about, like this Earth, okay. So if we kind of put this Earth as kind of a 1 meter kind of scale, and 1 nanometer means essentially, tennis ball or baseball, okay. So in the sense, like this 1 nanometer is actually very, very small object, right? Because, like 1 meter, I mean, if you guys are familiar with the ANSI unit, that is essentially about 3 feet, right? 3 feet. So 1 nanometer, like 3 feet, like Earth, and then if we downscale, like 10 to negative 9th power, that is essentially, the size of the baseball or tennis ball, okay? And or another way kind of thinking about this is, like if you look at this SEM image, okay, SEM is actually kind of a nanotechnology enabled tool to image very, very small scale objects, okay? And then in fact, we have actually SEM. How many of you guys have used SEM? Okay, great. So you guys know the power of SEM. And so, like using this SEM, they image the human hair, okay? So this is this thick one is a human hair, Okay, so human hair diameter is only about 50 micrometer. Okay, so it's actually quite small, but do you see other kind of fibers here? These are essentially, like a nanofibers. Okay, so nanofiber, if you look at it, diameter is much smaller than even human hair, right? And then this is essentially considered as nanomaterials. Okay, so in the sense, like this nanofiber, like for a single strand, you cannot see with naked eye. Okay, and you need a special tool to image it. And imagine, like, if you want to kind of align these nanofibers in a certain way, how can you do that, right? I mean, those are also kind of involving some nanotechnology. Okay. So why nanoscale is so special, or why nanomaterials are so special? First of all, property can be very different at the nanoscale. Okay, like this one kind of touches like basically every property. Okay, electronic, optical property, mechanical, thermal, and chemical. Okay, so in the sense, this one is really not just miniaturization. Okay, as you downscale, obviously miniaturization happen, but if you kind of bring the material to nanometer scale, actually new properties kind of emerge. Okay, so that is why nanotechnology is actually very interesting, and also it has a lot of opportunity. Okay, because think about it. For bulk materials, we already know almost all properties, right? And now, if you kind of bring those materials down to nanoscale, like a new properties kind of come out. Okay, so what that means is that we have more opportunity to engineer those properties, okay, and then kind of fine tune so that we can get desired properties. Okay. So previously, when there was not much nanotechnology available, what scientists have done was essentially kind of mixing materials together, right? Kind of creating alloys, right? But now with these nanomaterials, you can do a lot more, right? You can kind of tune the size, and you can kind of even at the nanoscale, you can still do alloy or even kind of doping, like etc. You can actually engineer properties in many ways. Okay, and also now we can talk about also miniaturization. Okay, as you kind of scale down, high density of structure is possible because we are essentially dealing with the smaller size. And also, scale at much biology works. Okay, that is essentially nano scale. Okay, for example, and as I mentioned, DNA width is 2 nanometer, and also cell membranes size is around 10 nanometer. Okay, so what that means is that, many of the bio engineering kind of deals with this nanoscale. Okay. And also, surfaces and interfaces play a large role at the nanoscale. Okay, so for example, like if I give you kind of perspective, imagine this 1 centimeter by 1 centimeter by 1 centimeter cubic. Okay, so this is essentially about ½ inch, right? ½ inch height, ½ inch width, ½ inch depth. Okay, and then for this cube, the total surface area is a 6 centimeter square. Okay. But let us now kind of cut it into 10 pieces in each side. Okay, so for example here 10 pieces, 10 pieces, and 10 pieces. Then when we kind of sum up all the surface area, now is basically 60 centimeter square. Okay, but now if we kind of keep doing this kind of cutting, okay, and then now if we create 1 nanometer cube out of this, like 1 centimeter by 1 centimeter by 1 centimeter cube. Okay, so then, if we sum up all the surface available from, like a very small cube, right, or 1 nanometer cube, then the total surface area becomes this 60 million centimeter, square. Okay, and then like this one doesn't. I mean, it has a value, but like this one, you guys don't feel how big this number is, and then actually it turns out this is essentially equivalent, almost equivalent to the size of a football field. Okay, so football field, this is area is essentially, 53 million centimeter square. Okay, so what that means is that, like now you are starting with this small object, right? Like half inch, half inch, half inch. But if you create 1 nanometer cube out of it, the total surface area becomes just like a, like a little larger than football field. Okay, so what does it mean? A lot of surface available, a lot of interfaces come out of this, individual cube, right? So what that means is that, like if the surface effect is important, for example, catalysis, okay, even with a very small quantity of material, you have so much surface area, and then you can actually accelerate the chemical reaction, etc., through catalysis. Okay, so this is why nanomaterials are also very important, for surface and interfaces. Okay. So up to this point, do you have any questions? By the way, if you have any questions, just stop me and then feel free to ask. Okay. And also, these are kind of some examples. Okay. So at the bulk scale, like just by looking at it, or our way of distinguishing is by optical properties, right? Like how can you tell between silver and gold? You can kind of look at the color, and then you can tell, okay, this should be silver and this should be gold, right? But if we actually make, like a nanoparticles out of silver and nanoparticles out of gold, these optical properties can be actually very, very different. Okay, for example, this is essentially, the silver nanoparticle, the size is only about, the diameter is like 20 nanometers, about that. Then if you kind of just disperse in water, and then if you look at the color is no longer silver color, right? I mean, like our common way of defining silver color. Okay, this is a silver, okay, but the color is more like a yellowish, right? And also, if we make gold nanoparticles, okay, and then now dispersed in water, okay, so then depending on the size of nanoparticles, okay, the color also changes. Okay, so this one is more like a reddish, and then this one is more like a kind of purplish. Okay, so as we make nanoparticles, or as we scale down materials, the typical optical properties is lost, and then new optical properties kind of emerge. Okay, so, and then by the way, this gold nanoparticle kind of this dispersion and then kind of observing the color change, we are going to actually do it in one of our labs. Okay, so you guys will get to produce gold nanoparticles later. Okay, and another thing is a melting point of gold. Okay, so for example, at the bulk scale, the melting point of gold is 1064 degrees Celsius. Okay, but if we make particles smaller and smaller, okay, like made of gold, and then now melting point starts decreasing quite a bit. Okay, so let us look at this kind of a plot here. So at 11 nanometer, right, the melting point is more or less like a very close 1064, right? Because this one value is about like 1000. I cannot really kind of draw the horizontal line there. So what that means is that like if you actually bring gold down to like a 50 nanometer, it'll still be 1064 degrees C, right? But if we make smaller and smaller, then like if we bring down to like let's say 6 nanometer, now melting point is somewhat smaller than 1064. But if we make gold nanoparticle that is very, very small, like the radius is only about, let's say, 2 nanometer, maybe it's a little bit less than 2 nanometer, and then for this size, melting point is only about 500 degrees, right? So this one clearly tells you, as you scale down, the material properties you observe at bulk scale, can be drastically changed, right? So you know, these are just kind of some of examples, okay? And also, this is a kind of a more practical kind of application, okay? So the example is optical disk drive, okay? So this is a CD-ROM, okay? I'm not sure if you guys still use a CD-ROM, like most of you guys use a DVD or Blu-ray now, right? And then the way it works is, I mean, it's basically the same idea, okay? So basically, this is a kind of top side. There is a label, okay, that you guys are seeing on top of this CD-ROM. And then below this label, there is a reflective aluminum coating. And then below that, there is a die, okay? And then below that, you know, I mean, there is a kind of another layer. But this die is essentially kind of used to store the data points, okay? Basically, you are creating 0 and 1, okay? Basically, digitizing. So the way you kind of do is that you are using the laser, okay? So for example, if you burn the die, okay, and then because if you burnt it, now it absorbs the light, then that is indicates basically 0. And then if this one is not burned, if you just leave it empty, what that means is that the light penetrate and then now reflected from aluminum layer, and then now this one is essentially kind of indicates 1. Okay, so you know, by like burning and not burning, you can kind of create arrays of 0 and 1, and then that is how you store the data and then read the data. Okay, so for this one, you know, like we need to look into electromagnetic wave spectrum. Okay, so if you guys remember, the visible spectrum is essentially from 400 to 700 nanometers. Okay, so this is a visual spectrum. And then, you know, below this 400 nanometer, that is essentially UV regime, right? And then above 700 nanometer or above this red spectrum, there is infrared, right? And then, you know, there are other also electromagnetic spectrums, okay, microwave, FM, and then if we for lower X-rays and gamma rays. Okay, but now let us just kind of focus on visual spectrum. Okay, so again, like if I just kind of reiterate, the higher wavelengths is essentially red. Okay, 700 is red, and then 400 is more like a violet. Okay. Okay. So the way we kind of advanced this technology was using different wavelengths of the laser. Okay. For example, for CD-ROM, you know, the laser wavelength was 780 nanometers, okay? And then as you know, like a CD-ROM, DVD, Blu-ray all have the same diameter, okay? Like typically, they have the kind of standard size, okay? So, and then the way they can store large amount of data is essentially by using the smaller wavelengths. Okay, so for example, for DVD, the laser they use is 650 nanometer, and Blu-ray they use a 405 nanometer. Okay, and then by reducing this wavelength of the laser, they were able to store, you know, before 700 megabytes only, but now 25 gigabytes. Okay, it's a substantial. And then why is that? That is because, you know, like if you use actually kind of larger wavelengths, then you can only define kind of a, you know, the resolution at a larger scale. Okay, but if you actually use the smaller wavelengths, now you can kind of finely store data and finely read the data. Okay, so this is related to diffraction limit. Okay, so basically, you know, like by using this smaller wavelength laser, you know, they were able to store large amount of data. Okay, so in the sense, you know, as you create final resolution, basically you store more and you know, you read more. Okay, so in fact, if you look at this 405 nanometer, you know, like what is the color of that? That is more like bluish laser, right? That is why it's called Blu-ray. Okay, because you know the laser they use is kind of blue. Okay, so obviously for this one, it's related to kind of a, you know, miniaturization, right? But that is essentially, you know, like how the nanotechnology enabled, you know, large quantity of data storage. Okay. So in fact, like this one also applies to, electronic devices, right? Now, computer, well, over the time, computer got faster and faster, right? And also we store more and more in, the same size hard disk drive or solid state drive, okay? The reason for that is because we are creating, smaller size of transistor, and then for a given size, for a given platform, we can input more number of transistors, right? So that's why we can achieve the high computing power and also higher data storage, okay? So basically that is how it works, okay? And then, like you might wonder, is the nanotechnology really new, right? But in fact, actually, nanotechnology is not really new. Arguably, okay. So why is that? If you kind of look at this stained glass from the early 15th century, okay. If you go to kind of old, ancient kind of cathedral or church, you guys see this stained glass, right? And then the way they prepare or the way they kind of made this stained glass in old age, they actually kind of did several experiments, okay, just by experience, okay? So for example, they found that if they add gold chloride, materials that contain gold chloride or add materials that contain silver nitrate, and they create some red tint color, okay? And also they add silver nitrate, they create kind of yellow color, okay? So, and then that is just by experience, basically they learned that, okay, if we add certain materials, we can create this color and that color. And then recently, scientists analyzed this tinted glass, and then they found these gold and silver nanoparticles, okay? So, that is essentially reflecting red and yellow light, okay? So, as we saw in 2 or 3 previous slides, you guys saw the colors of silver nanoparticles and gold nanoparticles, right? So in old age, even in 15th century, they were essentially producing silver nanoparticle and gold nanoparticles without knowing it, right? They were just kind of, by experience, they were producing this color, but it turns out, they were essentially producing nanoparticles, okay? So in the sense, but they just didn't know, right? Because there is no way to find out, but basically they were essentially producing gold and silver nanoparticles by experience, okay? But recently, scientists just proved that those contain nanoparticles, okay? And another example is Damascus steel, okay? So this is essentially from 8500 to 1750. It's a quite old technology, right? And then this one is actually known to have a very tough and resistant to shattering, okay? And also, it's capable of being honed to a sharp and resilient edge, okay? So, and this still kind of have some of them, basically found from the graveyard and stuff like that. And scientists have found traces of carbon nanotubes and nanowires present in Damascus steel blades. Okay, so again, they were producing this knife, made of Damascus steel. They just kind of practice and experience, how they can make a better blade, right? And then they were essentially kind of producing carbon nanotubes and nanowires, okay? So again, without knowing, these are present, just kind of by experimenting and experience, they were essentially making better and better material, okay? So secret recipe has been lost for centuries, but recently metallurgists kind of recreate the process, okay, to make this Damascus steel, which has excellent properties, okay? So obviously, we don't know whether this recreate process is identical to the one used in old age, okay? But now, if you actually go to some Williams Sonoma, whatever, you can actually see this kind of knife, okay? And then they advertise it has excellent mechanical properties, okay? So in the sense, you know, like in old age, you know, they actually use the products enabled by nanomaterials. Okay, so in the sense, this nanotechnology is not really new, but you know, this nanotechnology is actually kind of emerging as a kind of a you know, kind of a new opportunity, because now, you know, because of so much development, now they can really identify which materials are there, and they can even kind of you know, try to engineer so that it has even better properties. Okay. So then, you know, like another question you may have is, okay, so how did this nanotechnology start, right? So basically, you know, this one kind of goes back to 1959, okay, and then basically physicist Richard Feynman kind of you know, had a, you know, like a seminar, and he kind of asked audience, you know, like, can we write the entire 24 volumes of the encyclopedia on the head of a pin? Okay, I mean, obviously this one is so tiny, and how can you write all the information in this tiny, you know, head of the pin? Okay, so, you know, and then he kind of also suggested that it should be possible to make machines at the nanoscale that arrange the atoms the way we want and do chemical synthesis by mechanical manipulation. Okay, so at the time it was a really kind of a radical idea, right? Because, you know, like back then, you know, there was no technology available. Yeah, and, you know, back then obviously it was just an idea, because, you know, like we cannot see it, and then we cannot even touch it, we cannot even manipulate it. Okay, and then how can this be possible? But, you know, after this radical idea, you know, many scientists took a kind of a, you know, like initiative. Okay, and then, you know, like over the time, we made so much development. Okay, so, you know, like after this, not long after, you know, like in 1981. Okay, so that is just about what, like 22 years later, IBM developed a scanning tunneling microscope. Okay, this is called STM also. Okay, and, you know, because of this tool, this two developer, okay, or scientists, this Garbini and Heinrich Rohr, got the Nobel Prize in physics in 1986. Okay, so and then this is actually kind of interesting, because look at this one, 1981, the tool developed, but the developers got the Nobel Prize in just 5 years later. Okay, this one is a very short span. Okay, usually, you know, Nobel Award is given after, you know, many years. Okay, because, you know, like we need to prove that those ideas are valid, and, you know, kind of you know, like it just needs time. But it was given just 5 years later, and then you can see, you can or imagine how impactful this tool was. Okay, so, you know, this is actually the first STM developed by these two scientists. Okay, and by the way, have you guys heard about tunneling, electron tunneling? Okay, maybe you guys heard about it, but anyway, so we are going to learn more about it in this course. The way it works is that, you know, like if you bring the tip to the conducting substrate close enough, okay, but there is a still kind of insulating gap, okay, but if we bring the tip very close to the surface, conducting surface, electron can tunnel through the insulating layer. Okay, this might be absurd, right? I mean, like because the electron cannot pass through insulating layer. That is what we know, right, in Berg scale. But if we bring the tip to the surface at a very close kind of distance, for example, 1 nanometer, then electron can tunnel through it. Okay, and then that electrical current is heavily dependent on the gap between the tip and the substrate. Okay, so for example, if you widen the gap, electrical current drastically goes down, and then if we bring the tip to the surface closer, then electrical current exponentially increases. Okay, so what that means is that by changing the gap, or by maintaining the gap using the feedback, you can actually image atomic arrangement. Okay, so I'm not going into detail because we are going to get back to it, okay, later. But point here is that current, tunneling current, is very sensitive to the distance, and then with that you can enable the imaging of the atoms. Okay, so with this STM, scan tunneling microscope, they actually scan all the graphite, and then you can see kind of a hexagonal arrangement of the carbon. Okay, so this one was is a really eye breaking, really eye breaking because they enabled atomic arrangement for the first time. Okay, so and then this is only about 2 nanometer, and then this is 0.5 nanometer, and then each yellow dot represents carbon atom. Okay, so this is a current STM, okay, scanning tunneling microscope. Obviously, compared to the one developed in 1981, it's a lot more advanced now, okay, in terms of stability and drift, etc. Okay, and then with this current STM, now we are at a level where we can manipulate individual atom and then place in a desired location. Okay, for example, IBM, they manipulated individual xenon atom and then they wrote IBM. Okay, so this one is not, kind of just kind of computer image. This is actually imaging done by STM and also manipulated by STM. Okay. So in the sense, let me kind of show you this YouTube video. Okay, and this one. Yeah, let's take a look and then we can kind of discuss after that. Maybe I'll just pause here. Okay, so the way they did is actually this individual kind of ball shape is what? This is atom. Okay, so they actually prepared atomically flat surface first. I mean, that is also a very challenging part. Atomically flat surface, and then they are manipulating individual atom, and then take a frame, and then they manipulate another one, take a frame, and then they made a movie. Okay, it's like a stop motion, but it's at the atomic scale. Okay, and then see how finely tuned this movie is. Yeah, so basically that's it. So can you imagine, I mean, now we are at this level, like individual atoms can be manipulated and placed at a desired location, okay? So obviously, I mean, just this movie itself is really amazing, right? But there is also some limitation because they can only work with certain atoms, okay? So if you actually kind of, if you need to work with other types of atoms, then this manipulation is still not possible, okay? But with a certain atom, you can actually, manipulate and place in a desired location, okay? But can you imagine, if we can do this kind of manipulation for any kinds of atoms, right? If you can actually do that, then you can create new molecule, right? And then you can actually create kind of a, new types of materials, okay? But obviously, we are not at the level, and then many researchers are still kind of working toward that direction, okay? So, and that is that, and I think with that we can end here today, okay?